We've read in the data. Each example is now a list of tokens. But the problem is that we had a different data representation for trees, which is nested lists of lists of lists, in order to represent the trees that we can replace elements of in order to make little bugs into huge bugs. So what do? Well, since we've been careful about using data abstraction to write everything in terms of the functions tree, label, and branches, we could actually just redefine those in order to use the data from the file directly as trees. So we're trying to represent a little bug. We've read in a list of tokens that looks like this. I've put it into multiple lines just so that we can see what's going on. But Python's representation is just one long list of open parenthesis root, open parenthesis frag, etc., etc., etc. But this is actually a perfectly good representation of a tree. A long list of labels as well as parentheses that tell you where the branches begin and end. So, this entire list corresponds to the entire tree, but this smaller list corresponds to the branch of that tree. This smaller list corresponds to one branch of that tree. This smaller list corresponds to a branch of that tree, etc. You can even get down to this word a little representing a leaf of the tree. And why is it a leaf? Well, it's in this special position where it doesn't have an open parenthesis in front of it, so it's just a label on its own. Instead of trying to convert this long list into our existing tree representation, we're just going to use this list as our tree representation by redefining the tree, label, and branches functions so that the way we represent trees is just how they're represented in the file, as long lists of tokens with open and closing parentheses telling you the structure. So here's a redefinition of tree. It still takes in label and branches. We can't change that part because all the code we wrote to find the leaves, print out the words, change little bug into big bug relies on this signature. But we can change everything in here, and so here's the plan. If we're at a leaf, we just return a list with the single label, like the word little. Otherwise, if there are branches, then we return a list that begins with an opening parenthesis followed by the label, that's the root label of this tree. And then we put all of the elements of the branches into that list and end it with a closing parenthesis. So this noun phrase has an opening parenthesis, a root label, NP, followed by all of the tokens for the branches. There they are, there they are, there they are, and then a closing parenthesis to end the noun phrase. So here's the file we've developed so far, and we're just changing our data representation. If not branches means that we have no branches, then we return the label in a list. Otherwise, we need to build up a list that has an opening parenthesis to let us know that it's a non-leaf tree. It has the label in it. We take all of the elements of all of the branches, which themselves we're now assuming are lists of tokens like open parenthesis and close parenthesis, and put them in a long list. Sum does that for us. As long as we start with an empty list, we're going to build up a long list with all the elements of the branches that were passed in. And then we need to make sure that everything is balanced using a closing parenthesis. Now, how do you get the label out if this is your new representation of a tree? Well, if it's a leaf, meaning the len of the tree is 1, then the tree is just a list containing the label and nothing else. Otherwise, we can get rid of that part. We should expect that the first element is an open parenthesis. And it's not a bad idea to put an assert statement in there so that if for some reason this doesn't all work out, we'll see what's wrong. But this assert statement shouldn't do anything. Instead, it should just check to make sure that the open parenthesis is there and the label at the root of the tree follows directly after that. Our old definition of tree involved using isTree. But now we don't really need isTree anymore, so it's gone. isLeaf is defined in terms of branches. Leaves is defined in terms of isLeaf and label and branches. So these really are not part of the representation. They just use the representation, which means the last thing that we need to do is define the branches of a tree that's now represented in a different way. So before we fill that in, let's look at what a tree looks like. I don't have to change this part of my code at all. I can just look at it and figure out now what's the representation of this example. And since I redefined tree, I can see that it's now a long list, very similar to what we found in the file that we read. And we have to get out the branches of this. The branch of this should be everything that's not including the frag root label, and it should be a list of trees, which each is a list of tokens. So we somehow need to split this part up into a list of lists. Let's switch back to the slides and take a look at how we'll do it. The way we're going to find the branches of any particular tree is we're going to go through and look for matching parentheses. We're going to keep track of the current branch as we go through, as well as all the branches we've found so far. And we're going to start at element at index 2, because this is not part of the branches, that's for the whole tree, and this is the root label for the whole tree. The branches start here. So we'll just work our way along, adding the elements of the tree to the current branch until we notice that parentheses have been balanced, at which point we'll add that as a branch. Now we can start over building the next branch. Here we go, JJ Little. We've gone through and found another pair of matching parentheses, so we add that to the list of all the branches and clear out current branch in order to keep going. The last element we processed was here, so now we're at this open parenthesis, and in bug, ending, we find another set of balanced parentheses, that's a third branch. Here's our representation of the branches of the tree. Each of these is a tree in our new representation. Okay, now it's time to write some code to implement that process. If the length of t is just equal to 1, meaning it's a leaf, then we return an empty list of branches. Otherwise, we need to keep track of things. First of all, we need to keep track of how many parentheses have been opened but not closed yet. In the beginning, that should be 1 because t0 is equal to an open parenthesis. That should be true of anything that's not a leaf. We also need to keep track of the current branch, which begins empty, and the list of all branches, which begins empty. Then we go through the tokens in T. Now here's a representation for a tree. The branches don't start until index 2. So let's start there. We always want to append to the current branch the token that we observe. If that token is an open parenthesis, then the number that we have opened but not yet closed is going to be increased by 1. Otherwise, if the token is a closed parenthesis, then the number that have been opened but not closed is decreased by 1. And if it's the case that the only thing left open is the original opening parenthesis at the very beginning, then we found a branch. If opened equals 1, then we append to all branches the current branch. And we also start a new branch by setting this to empty. At the end, it should be the case that opened is down to 0. Why is that? We should have closed all the parentheses that were opened. At which point we can return all the branches, and we've implemented the branches selector using this new data representation. So, If we have an example that looks like this, then the branches of that example is a list. In this case, there's only one branch, so we can get branch at index 0. It has branches because that's a tree. We could get the branch at index 1. It has branches because it's a tree. And its only branch is a leaf. So if we get the element at index 0 of that list of branches, we can get its label and finally find a word, or we can show that it's a leaf. So that's great. Our branches function seems to be working correctly, but the implication is that we now have a new implementation for the tree data abstraction, which means that given an example, we can get the leaves of that example without changing the leaves function at all. We can get the words in that example. We can even replace in that example the adjective with huge, which gives us a new tree under our new tree representation whose words are a huge bug. But what's even cooler than that is that all the trees in the file, including, for example, tree number 123, a rabbit, are trees according to our representation. So I could get the root label of that, I could get the words in that, and now I have lots of different sentences represented as trees that I can manipulate using replace.